Today I wanted to have a quick run through this RA2822 test case. This is a 2D test case, and so there's some slight changes that are required to do a 2D test case. So unlike the Cartesian version of UFO-CFD, can't just take a simple slice, a 2D slice, because it's the octree version. Then you need to do a 2D section. So what that means is you have to you need to set up the geometry and the input file in such a way that it's suitable for a 2D octree mesh. So the geometry is this airfoil, like that, and the octree mesh ends up looking like this. So it's creating a normal 3D octree mesh, but then the user's limiting the size of the mesh in the Z direction. So you have to specify Z min and Z max. So if we take a quick look at the mesh that you end up with, get rid of the dead cells. So this is what you end up with. The reason why 2D is a bit more tricky with octree is because the mesh can only be as thick as the largest cell. So on the outer boundary where you've got these large cells, then that's how thick the overall mesh is. But obviously if you zoom in, into the airfoil, the mesh the airfoil has got many cells going across it, because the cells are much smaller here. So even though it's essentially a 2D validation case, you end up with quite a large mesh because it's an octree mesh. You've got a fine mesh near the airfoil which has to extend in the Z direction. So there's been a couple of changes made to the input file and to the solver in order to allow to do a 2D test case. So if we have a quick look at the input file, and that's the geometry, RE2822 case 9. We've got 11 refinement levels, and that's at the airfoil surface. And then we've got the background mesh, the largest cells are level 4. I've got 4 blanket layers as well. So we've ended up having to set the octree limit to 2 million. That's the total number of octree cells. And the octree point limit to 6 million. So the usual settings are specified here. 20,000 iterations required for this case, although the solution looks pretty good after 10,000 iterations. 2D smoothing, you have to specify 2D smoothing rather than 3D smoothing for this case, so that's one change. CFO number, smoothing parameters. The wall function I specified at 0.97 for this case, just to reduce the near wall velocity a little bit. And then going down, we've got the free stream conditions here. For this case, it's about Mach 0.73. So So that corresponds to 248 meters a second. And the other change at the bottom here, Z min is 0, Z max is 0.625. So that's what I was just talking about. That's the extent in the Z direction. And I've also added a refinement box to this test case. So I've selected the refinement level of 9, and then I've specified a refinement region. I've done that in order to add a bit more refinement in this area, because this is where you've got the shock wave and you've got a high speed region on the top here. So I've added a bit more mesh there just to improve the solution. So that's a refinement box that we specify in the input file. So that's about it. So this case takes a while to run, because there's about about 500,000 cells. So it does take a while to run. So look at the convergence. Convergence file has disappeared. And if we look at the solution, in PowerView you can load up a state. So if I load up a previous state, this is the solution, and this is how you do the validation based on the UFO-CFD type BTK file. So loading the octree mesh, take the threshold and set that the LCD to 0. So we're just looking at the cut cells. So that's eliminating the live cells and the dead cells. So that's what we're looking at here, is just the cut cells. And then you apply cell data to point data, which you need to do to be able to plot the results. So then specify your pressure coefficient. For this case, pressure minus reference pressure divided by dynamic pressure, half rho v squared, and that gives you your CP. And then plot on intersection curves. So that's this plot on intersection curves feature. So that takes a cut plane through the mesh that's currently being displayed, and then it plots the result on that. So I've got a Z cut plane, and it's plotting the result on there. So when you do plot on intersection curves, you have to select a Z normal to get the Z cut plane. Then you have to specify x-axis data 0.0, so that's your x coordinates. And then you deselect everything except your CP, and that allows you to plot the CP. So once you've got that CP plot on the right, then you can overlay that with your experimental data and do the comparison. So that is a very quick tutorial on how to do an airfoil validation case in UFO-CFD.